Welcome to Mr. Mac's Physics channel. He can explain things really well, and is a lot of fun to watch.
From the universe to the atom, this is our last inquiry question, and it has to do with looking deep inside the atom. And here are the outcomes that we need to achieve. And you'll notice in this, there aren't any formulas that are there. And yet the concepts are quite deep, and particularly when we come across standard model of matter. So the inquiry question is, how is it known that human understanding of matter is still incomplete? And again, we're looking at evidences. And so we're learning to investigate the standard model of matter with quarks or quarks, depending on your pronunciation, hadrons, leptons, and fundamental forces. And we'll be able to analyze the evidence for the existence of subatomic particles other than protons, electrons, and neutrons, which we've already looked at. So the question is, are they the smallest subatomic particles? And what evidence is there that suggests that protons and neutrons are not fundamental particles? And what evidence suggests that the existence of smaller subatomic particles? So the key to this is that we're looking at discovering particles that are not easily detected. And there's a whole history, as we'll see here. Going right back to John Dalton, he had an assumption that atoms were indivisible, but he also then came up with the law of multiple proportions, which is used heavily in chemistry. His experiment that actually supported that was reacting nitric oxide and oxygen to produce a gas that was consistent with the law of multiple proportions. Now, in physics, we've seen Röntgen with X-rays, discovering X-rays. We've seen J.J. Thomson with cathode rays and determining a value of the electric charge over mass for an electron. We've understood a lot about Einstein's explanation of the photoelectric effect. We've looked at the Geiger-Marsden gold foil experiment and how Rutherford used that to explain the results, showing a very concentrated, positively charged nucleus. And then we've also had a look at Chadwick's discovery of the neutron, where beryllium was bombarded with alpha particles. But in 1932, which is the same year as Chadwick made that discovery, Carl Anderson explored cosmic rays and discovered the positron, which are positively charged electrons. And Murray Gell-Mann and George Zweig independently discovered quarks. Now, Murray Gell-Mann actually made up the word, and he actually wanted it to be pronounced quarks, as in K-W-O-R-K-S, quarks. It's a moot point. Call them quarks, call them quarks, just we're going to learn how to use them. So he proposed quarks, and that's what I'll call them. And in 1968, a series of electron-proton scattering experiments at SLAC, Stanford Linear Accelerator Center in the USA, showed the inner structure of nucleons. So there's a very quick overview of experiments and discoveries from fairly famous people. Well, let's have a look at our first example for this inquiry question. And this will recall some of the formulas that we used in determining nuclear decay and nuclear reactions. So one of the implications of the grand unification theories is that the proton should decay with a half-life, get this, on the order of 10 to the power 32 years. Well, if that's true, Ed Kearns of Boston University actually found out the number of protons in a detector volume of protons was 7.5 times 10 to the 33. So how he counted them, probably picked them out one by one. Given that the constant of decay, and remember this lambda is not a wavelength, the constant of decay equals 10 to the negative 33, and the units are per year. The question is, calculate for 3 times 10 to the 33 years of observation the number of expected proton decays. So you may recall, there's the data from the question, you may recall this formula from our work with nuclear reactions and nuclear decay. So radioactive decay fits that model, but so does the decay of protons, as we'll see. The question is actually harder in concept than the maths is to calculate. So NT equals 7.5 times 10 to the 33, just substituting, times e to that power. So substitute for lambda, which is the constant of decay, and substitute for t, the number of years. And thankfully, those powers of 33 and negative 33 cancel really nicely, and we end up with 3.73 times 10 to the 32 as the number of protons remaining. So there's worked example 1. So the number of expected proton decays is N0, the initial amount, minus NT, which is 7.13 times 10 to the 33. I'm just going to move on a little bit and talk about leptons, quarks, and bosons. And this picture here is the standard model of matter. And we'll notice that some of these we're familiar with, we've seen them before. For example, in the left-hand column in the green is the electron. We know that electron is a fundamental particle. But we also have come across things like photons in the orange column, the 4th column there, the 2nd one down. We've also come across muons, and we can see neutrinos at the bottom. We're going to have to understand a little bit about this as the standard model of matter. And particle physicists actually use this table to describe the behavior of all known subatomic particles. So it's a theoretical framework, and it's useful for looking well within the atom, and all of these are fundamental particles, although the word particle is probably used in inverted commas. They do make up matter, but all the matter that we see and feel around us is from the first column only. In fact, the up and down quarks and the electrons are all that you need to make up atoms. The model incorporates quarks and leptons as well as their interactions through strong, weak electromagnetic forces. So strong nuclear force, weak nuclear force, and electromagnetic forces. The standard model puts field theories of quantum electrodynamics and quantum chromodynamics under one umbrella. And the one thing that's not under the umbrella is gravity. Gravity remains outside the standard model. Now, at the moment, you may be going, hang on, there's a huge jump from protons, neutrons, electrons. What is all the rest of this stuff about? You know, what is an up? What is a down? Well, let's have a look at a little bit more detail. You will need to learn this. You will need to learn the structure. And the question I've got at the top there, how can we remember this? Well, up and down are opposites. So, and that's a quark. So an up quark and a down quark. Charm and strange are sort of opposites. They're actually named for that sort of reason. Top and bottom pretty obviously are opposites. So those are all quarks. Then we have pairs. We have an electron and an electron neutrino. So we're just adding the word neutrino, and that's a lepton. We have muons and muon neutrinos, and that's also a lepton. We have tau and tau neutrinos, and that's also a lepton. And then we have, on the last column, gluon, photon, boson, and one of them is a Z boson, and the other is a W boson. And these are called gauge bosons. And notice they all end in ON. And then we have a Higgs boson, which is just something totally different. At this stage, we will try and learn all those different names, and then we'll look at the scientific evidence that supports the standard model and the existence of these up-down, charm-strange, top-bottom leptons, gauge bosons, and the Higgs boson. So here's how we go. If you have a piece of paper that's blank in front of you, this is how you learn the standard model of matter. First of all, draw 6 purple boxes, and then 6 green boxes underneath, and then 4 orange boxes on the right-hand side and 1 yellow box. Now, if you don't have those colours, that's okay. You can use a black pen, because in the exam, of course, that's what you'll be using. But the idea of the colours is to separate out the different categories. So the 4x4 boxes and 1 box on the side look like that. And you can see 6 purple boxes, 6 green boxes, 4 orange boxes that are vertical, and 1 yellow box. And the next step is to fill in the charges. Now, each of these have charges, but not quite as we know them. So some quarks are 2/3 and others are -1/3. Some leptons are -1 and others are 0. And all bosons are 0 except the W boson, which has, strangely enough, a plus or a -1 charge. So we fill those in. And you can see along the top, all the quarks are 2/3. The next row down, all the quarks are -1/3. Underneath that, all 3 of those are -1, and the bottom row, all 3 of those are 0. Going down the orange, we go 0, 0, 0, and then the bottom one is plus or -1, and the Higgs boson on the right-hand side is 0. Those are the charges. Now we fill in the spin. Now, the spin, just to think of it, to give yourself a conceptual understanding, think of a spinning top. And sometimes they spin one way, sometimes they spin the other way. So all fermions have a spin of 1/2, all bosons have a spin of 1, and the Higgs boson has a spin of 0. And here they are. So all the purple boxes have 1/2. All the green boxes have 1/2. All the orange boxes have 1, and the yellow box, the Higgs boson, has a spin of 0. Now we're going to fill in the correct names, and the name of the 4 bosons, that's the gauge bosons, which are orange, and the last boson, which is the Higgs boson. So here we go, here are the names. Hint, they all begin with Q, L, GB, and HB. Here we go. So you'll notice up the top of the screen, it says fermions, they're everything on the left side, and bosons, everything on the right side. So here are the names. So you can see the purple boxes are quarks, the green boxes are leptons, the orange boxes are gauge bosons, and the yellow one is the Higgs boson. And here are the answers. Now, what I'd like you to do is spend a minute or so filling in the names. They do have symbols. You've seen them before. So obviously the E for the electron, mu for the muon, nu, which is a Greek letter, for neutrinos, and then they're given subscripts. What you probably haven't seen before are the UDCSTB and the gamma for a photon, but that you've seen gamma rays, and that's what is designed there. So we think of electromagnetic radiation, we think of photons, and that's going to be the next little link between these 17 fundamental particles and the 4 fundamental forces of the universe. I'll say that again. Here is the link between these 17 fundamental particles and the 4 fundamental forces of the universe. If you haven't jotted it down at this stage, you can always rewind the video and jot them down again. The standard model, and if you look on the right-hand side, you'll see a diagram with 4 little diagrams. There's a strong nuclear force that binds the nucleus together. This is why 2 protons sitting in the nucleus don't fly apart. There's a weak nuclear force that occurs in the nucleus that causes the nucleus to decay. It's fairly random as to when it happens, but in general we talk about a half-life. There's the electromagnetic force that binds atoms together, so the proton is pulling the electron towards itself, and that's the same force that governs all electrical fields and magnetic fields and electromagnetism that we looked at in detail. And the last one is the gravitational force that binds, if you like, everything in the solar system, everything in the universe that we've seen right from the word go when we've been dealing with gravity. The standard model explains how the basic building blocks of matter interact and are governed by fundamental forces. The 4 fundamental forces at work in the universe: strong force, the weak force, the electromagnetic force, and the gravitational force, and they work over different ranges and have different strengths. Gravity is, surprisingly, the weakest, but it has an indefinite range. Electromagnetic force also has an indefinite range, but is many times stronger than gravity. The weak and strong forces are effective only in very short range and dominate only at the level of subatomic particles. Despite its name, the weak force is actually much stronger than gravity, but it is indeed the weakest of the other 3. The strong force, as the name suggests, is the strongest of all 4 fundamental interactions. But the range that they act over, the strong force, is within the nucleus. You might want to think of it a bit like Velcro. Velcro acts very, very close. It's quite strong, but when you pull it apart, it has no effect. So the 4 fundamental forces can be pictured like this. Here's the strong force, the force which holds the nucleus together. Call it strength 1. It has a range of about the diameter of a medium-sized nucleus. And the particle associated with it are gluons and nucleons. The second is the electromagnetic. Its strength is about 1/137. And its range is infinite. The particle that communicates, if you like, this fundamental force is, of course, the photon, which has a mass of 0 and a spin of 1. The third is the weak nuclear force, and neutrino interaction induces beta decay. So we're looking at decay of the nucleus. The range is very, very small. It's about 0.1% of the diameter of a proton, which means 10 to the negative 18 meters. It's dealing with intermediate vector bosons, which are W+, W-, or Z0, with a mass of just greater than 80 gigaelectron volts and a spin of 1. And the 4th fundamental force is gravity. As we've said, it has an infinite range. Its strength is 6 times 10 to the negative 39. And you should recognize the order from our formula and data sheet. The particle is, at this point, theorized to be a graviton with a mass of 0 and a spin of 2, but as yet, this is undetected. Now let's have a look at a worked example. And this is a 2-mark question. Identify the fundamental forces proposed by the standard model of the atom, and explain, for 3 marks, how the stability of atomic nuclei is maintained. Well, here's the answer. There are 4 fundamental forces. and the strong force that holds nucleons together, the electromagnetic force that attracts and repels charges, the weak force that binds electrons and neutrinos in the nucleus, and the gravitational force that attracts masses. The standard model of the atom explains the interaction of the basic building blocks of the universe and the interaction of the fundamental forces, except the force of gravity. So how do we explain the stability of the atomic nuclei, how it's maintained? Well, since protons have a positive charge and electrostatic force cause positive charges to repel each other, it's expected that the nucleus would be unstable. It'd fly apart. The strong nuclear force in the standard model of the atom causes particles to be attracted together, thus maintaining stability of the nucleus. Baryons are composed of 3 quarks. Protons are 2 up quarks and 1 down quark. Neutrons are 2 down quarks and 1 up quark. Quarks have a quality called color that holds quarks together. Gluons are bosons that carry this color force over tiny distances. So gluon exchanges between the quarks within protons and neutrons are responsible for the strong nuclear force that keeps quarks together. Gluon forces between baryons are mediated by mesons called pions, which consist of a quark and an antiquark pair. Interactions of pions between baryons help to provide the glue, in inverted commas, or strong force that holds neutrons and positive protons together. Stable nuclei have an appropriate ration of protons and neutrons, thus enough gluon and meson interaction to overcome the repulsive electrostatic forces between protons. Therefore, the nucleus is stable. So we're dealing with quantum physics, and that describes the nature with wave function used in Schrödinger's equation to describe the fundamental particles and forces. This wave function predicts the future behavior of a dynamic system. It predicts analytically and precisely the probability of events or outcomes. And particles are subject of the search for elementary particles. Particles are made up of quarks and leptons. Particles may be classified as fermions or bosons and as matter and antimatter with interactions pictured by Feynman diagrams and explored using accelerators. Quarks are held together by gluons. Quarks come in 6 flavors: up, down, charm and strange, top and bottom. Quarks come in 3 colors and interact by the color force, which is the origin of strong interaction, and by all the forces, including gravity via gravitron. Quarks in pairs make up mesons, and in 3s make up baryons, which are both included in hadrons. Now, there are a lot of new terms that we're suddenly introduced to, so it's probably best that we come to another worked example. And this comes from the 2020 HSC paper. Describe the hydrogen atom in terms of the standard model of matter. This is a good question to reveal a student's understanding. It's worth 4 marks. And you can see the answer coming through now. The hydrogen atom is composed of a proton nucleus and an electron. So always start with stating explicitly what might be assumed or obvious. A proton is a hadron consisting of 3 quarks, 2 up quarks and 1 down quark. The quarks are bound together through the strong nuclear force. The electron is classified as a lepton, a fundamental particle that can be isolated. Now, in answering this question, the markers have said you could have talked about fractional charge of quarks, or the role of electromagnetic force, or force-carrying bosons. But those 4 sentences would get you the 4 marks. Said in better responses, students were able to correctly describe the quarks, leptons, and bosons associated with the hydrogen atom. Areas for students to improve include applying the standard model of matter to the whole hydrogen atom. So you had to mention the proton, you had to mention neutron, you had to mention the electron. And also correctly associating specific bosons with fundamental forces. So you had to mention electromagnetic force. Work example 3 has to deal with particle physics. And it says, use the diagram to outline one way in which physicists obtain particles with appropriate energy to investigate the structure of matter. And it's worth 2 marks. The diagram about to show you represents the basic features of a particle accelerator, such as the Large Hadron Collider at CERN in Geneva, Switzerland. In the world's largest, most powerful particle accelerator with a 27-kilometer ring of superconducting magnets with a number of accelerating structures to boost the energy of the particles along the way. And so here's a diagram. If you were given this question in an exam, you would need to identify the Large Hadron Collider. That's important. Location in CERN, C-E-R-N, is the initials of the organisation, in Geneva, Switzerland. To refer to its 27-kilometre ring circumference, and also to be able to just simply draw something of the LHC with some of the details that you can see in this diagram. So you can see that there are 4 orange experiments. You can see that there are smaller circles that accelerate the particles, and you can see that the blue one says speed equals fast, the yellow one says speed equals faster, and the orangey pink one says speed equals really fast. And you'll notice that they collide particles and then detect what happens. So we're not looking for a detailed description of the latest that's happening at Large Hadron Collider. We're just simply wanting to outline what is used to find evidence for investigating these fundamental particles of matter. And as we continue with this example, if I can, the accelerator, what happens is protons and antiprotons are produced and released from source rooms. The particles enter an evacuated hollow container that forms a large circle, a bit like a donut. Inside the tube, magnetic fields control the charged particles as they travel in opposite directions, but they do not collide. Particles receive a boost to travel near the speed of light, and then in a target room, they collide head-on. Sensors in the target room give data for physicists to understand more about the structure and composition of matter. So there's that diagram again. Now, the proton, we've already mentioned that it contains 2 up quarks and 1 down quark. And if you add up the charge, remember the charge on a up quark is positive 2/3, and multiply that by 2 and add on a down quark charge, which is negative 1/3, and you'll get a positive 1 charge. So protons and neutrons that make up the nucleus are held together by the strong force. A proton is a baryon. Remember, baryons have 3 quarks. The proton is composed of 2 up quarks and 1 down quark. So the charge equals, there's a simple addition and subtraction, plus 1. It has a spin of a half. Now the neutron is also in the nucleus, and it's held together also by the strong force. It is also a baryon made up of 3 quarks. 2 of them are down quarks and 1 of them's an up quark. And the total charge there, 2/3 minus 1/3 minus 1/3, is 0. The neutron, as Chadwick discovered, is neutral. It also has a spin of a half. So here's a worked example. Explain how protons and neutrons end up with their charge values in terms of their quark composition. Well, each quark has a charge. An up quark is plus 2/3 and a down quark is minus 1/3. A proton is a baryon and is composed of 2 up quarks and 1 down quark. And so 2/3 plus 2/3 minus 1/3 is plus 1. Thus, a proton has an electric charge of positive 1. A neutron is a baryon and is composed of 1 up quark and 2 down quarks. 2/3 minus 1/3 minus 1/3 is 0. Thus, a neutron has no electric charge. And the little graphic at the bottom right, you can see from macroscopic a sandcastle to microscopic with the sand grains, and then the crystal and the crystalline structure going down to the atom, the atomic nucleus, the nucleon, and then the quark. Remember that quarks and electrons are fundamental particles. Now let's deal with the electron and positron. As one of the leptons, the electron is viewed as one of the fundamental particles. It's a fermion of spin 1/2 and therefore constrained by the Pauli exclusion principle. This has key implications for the building up of the periodic table of elements. The electron's antiparticle, which is the positron, is identical in mass but has a positive charge. If an electron and a positron encounter each other, they will annihilate each other with the production of 2 gamma rays, and we've already seen that. The Pauli exclusion principle applies to ionic bonding, covalent bonding, nuclear shell structure, and nuclear binding energy. Simply put, no 2 fermions can exist in identical energy quantum states. So no 2 electrons in an atom can have identical quantum numbers, and that guides the modelling of the build-up of the periodic table. When applied to solids, no 2 electrons in a solid can have identical energy states. This leads to the concept of the Fermi level and or band theory in solids. Electron degeneracy governs the collapse of stars to the white dwarf stage, so it applies to stars. And neutron degeneracy governs the further collapse of stars to the neutron star stage. So what we see in the subatomic particles applies to the macro universe with white dwarfs and neutron stars. Positron annihilation, as I said, we've seen this before. When positron and electron annihilate each other, then energy is given out. So the positron is simply the antiparticle of the electron. When a positron enters any normal matter, it will find an abundant supply of electrons with which to annihilate. The energy released by the annihilation forms 2 highly energetic gamma rays, and those 2 gamma ray photons must travel in opposite directions in order to conserve momentum. When a photon has quantum energy higher than the rest mass energy of electron plus a positron, one of the ways that such a photon interacts with matter is by producing an electron-positron pair. And we saw this back in inquiry question number 1. So here's a worked example. It says, describe with examples what antiparticles are and the result of a particle and its antiparticle interacting with each other. So here's the answer. An antiparticle is like a mirror image of a particle. Now, that's an analogy, so we won't push it too far. It has the same mass, but it is opposite in all its quantum properties. For example, a positron is an anti-electron with a positive electric charge instead of obviously a negative. The result of a particle and antiparticle interacting is that they will annihilate each other. The total mass will be converted to gamma rays according to Einstein's energy mass equivalence formula, E equals mc squared. And so you can see a diagram there of matter with protons and electrons, and antimatter with an antiproton in the center and positron. Well, I hope you're not getting a headache like this man. What are hadrons, baryons, and mesons? I've mentioned them as we've gone through the description. And there are 3 more diagrams. Any one of them is useful. It's just different ways of trying to explain the same thing. So we're trying to summarize the fundamental particles, and in doing so, we're categorizing them. Hadrons are particles containing quarks. Okay, so hadrons are particles containing quarks. Baryons are hadrons containing 3 quarks, and mesons are hadrons containing a quark and an antiquark. The 3 classes of particles are hadrons, mesons, and baryons. Hadrons are particles that experience the strong nuclear force. This means that they contain quarks. A baryon is a type of hadron, and it contains 3 quarks. A meson is also a type of hadron, and it contains 1 quark and 1 antiquark. Well, predicting particles, and this is some wider reading that is useful to put into those open-ended questions. This man, Hideki Yukawa, in 1935 reasoned that the electromagnetic force was infinite in range because the exchange particle was massless. He proposed that the short-range strong force came about from the exchange of a massive particle, which he called a meson. In 1937, a particle of mass close to Yukawa's prediction was discovered in cosmic rays by Anderson and Neddermeyer, and by Street and Stevenson in independent experiments. This particle, the muon, turned out not to interact by the strong interaction. Hans Bethe and Robert Marshak predicted that the muon could be a decay product of the particle sort. In 1947, Latz, Muirhead, Occhialini, and Powell conducted a high-altitude experiment flying photographic emulsions at 3,000 meters. These emulsions revealed the pion, which met all the requirements of the Yukawa particle, or the particle that he predicted. We now know that the pion is a meson, a composite particle, and the current view is that the strong interaction is an interaction between quarks, but the Yukawa theory stimulated a major advance in the understanding of the strong interaction. Then we come to ANSTO, and this is an important understanding of cyclotron. You can see a diagram in the top right. The National Research Cyclotron Facility is part of Australia's national research infrastructure, and it produces radioisotopes used in combination with nuclear diagnostic imaging. The ANSTO facility at Camperdown, so this is next to the University of Sydney, just about the heart of Sydney, produces radioisotopes exclusively for research purposes. So what is it? A cyclotron is a particle accelerator. It's an electrically powered machine which produces a beam of charged particles that can be used for medical, industrial, and research purposes and processes. Cyclotron accelerates charged particles in a spiral path, which allows for a much longer acceleration path than a straight line accelerator. So essentially, we've got particles that are going around in circles, starting in the source in the center and spiraling outwards until they're finally released to hit the target. The cyclotron body consists of electrodes in a vacuum chamber, and that vacuum chamber is flat and sits in a narrow gap between poles of a very large magnet, which creates a perpendicular magnetic field. So when the stream of charged particles is fed into the center, and a high frequency oscillating voltage is applied across the electrodes, the voltage is alternately attracting and then repelling the charged particles and causing them to accelerate. So you could see that as the oscillator attracts and repels the particles, each time it goes past the oscillator, those charged particles accelerate, and because they're accelerating, they then move to a larger radius until they get to a point where they exit the cyclotron as an exit beam and hit the target. Come back to CERN, and you'll see an aerial photo that shows the bottom western part of Switzerland and bordering France, and the LHC is the Large Hadron Collider. And there's some information to look up in your own time for the new one, the new particle accelerator. That is absolutely gigantic, and you can see the relative sizes of the two circles. And our last one for this afternoon, worked example 6, says explain using an example how a particle accelerator has provided evidence for the standard model of matter. And again, this is from the HSC question from 2020. So here's the solution. A linear accelerator was used to provide electrons with sufficient energy to penetrate protons. The scattering of these electrons was consistent with the protons having an internal structure. It was then inferred that the proton itself was not an elementary particle, an observation that contributed to the idea that protons were made up of quarks. And here's some comments from the markers. Better responses, students were able to provide a relevant example of experimental evidence and use cause and effect statements to provide a coherent explanation. Areas for students to improve include demonstrating a clear link between the result of an experiment and how it supports a named aspect of the standard model of matter. And you can see this is an open-ended question, and I'm just going to stop sharing that now. And one of the most important things to realize is that we're learning new things, albeit in the last week of term, but we need to be able to apply that to questions using the same sort of skills that we've had before. So if it's an explain question, that we put in causal language. And if it's a describe question, we are very accurate in our descriptions and colourful with adjectives.